All right, thank you everyone for coming. And I'd like to thank the organizers for inviting me to speak here. I'll be giving 2 lectures, one today and the other one tomorrow. So today I'm going to talk about joint work with Mikolaj Fraczyk, and also joint work with Samuel Edwards, Mikolaj Fraczyk, and Hyo. All right. So this. I gave the same talk in like a month ago in ICERM, and there's some overlap. And I have to apologize. You will see the same talk who was in the ICERM, but tomorrow will be a new talk. So if you are there, then you can just wait until tomorrow. All right. All right. So I would like to start with a question. So here's the setup. So you have my G is going to be high rank. High rank semi-simple Lie group. And I'm going to consider a discrete Zariski dense subgroup. So suppose you have a discrete Zariski dense subgroup gamma, and this is a lattice, or lattices in G are large discrete subgroup because lattices fill the ambient group. Now my question is the following. So question is, can you find a large Zariski dense discrete subgroup which is of infinite covolume? So this is my question. So is there a Zariski dense discrete subgroup gamma inside G that has infinite covolume? Oh, sorry. So is there a large Zariski dense discrete subgroup of infinite covolume? And well, the second question is, what does large mean here? And the answer to my question is I don't know how to answer this question too. And I would like to answer this question in a certain sense. So what do I mean by this? So suppose you have a lattice inside higher rank lattice. Higher rank lattice inside G. Then we more or less know the structure of the higher rank lattice by Margulis arithmeticity theorem. So higher rank lattices are understood by Margulis arithmeticity. But in contrast, for the infinite covolume discrete subgroup, there seems to be not much theory that is well developed. So in contrast, much less or not much general theory.
I'm sorry, I don't understand that comment. I mean, isn't everything we've been talking about that theory?
I'll get to this point. So not much general theory is. That's a very.
So it depends on what you want to understand, right?
Everything.
Well developed. but there are special cases which is well studied, which is one of the topic of this workshop. So special classes of subgroups are well studied. And notably, analogue subgroup. Are you fine now?
Yeah. Well, I'll get over it.
Okay, so yeah, this is workshop on analogue subgroup. So all right, but yet we still don't know many constructions. So still not many constructions seems to be known. Yeah, so what yeah, what do I want to say? We want to, so the motivating goal is to get a better understanding of discrete subgroup of infinite covolume. In particular, why are we lacking such examples of infinite covolume discrete subgroup? So that's one motivating goal of. I mean, I don't want to say like that I know how to like answer this or anything. So in my first part, joint work with Mikolaj Fraczyk. So we give a method using entropy rigidity of Einzler-Katok and Einzler-Katok-Lindenstrauss, where you leverage this entropy rigidity theorem to gain some better information about this discrete subgroup of infinite covolume in certain case, and we hope to see more application so that we want to maybe know in the future, maybe we can answer, maybe using our method, can we say something about, to some extent, what the large Zariski dense discrete subgroup, like what the constraint should be. So this is the motivation for this. And also we have a second part, which was done by Sam Edwards, Mikolaj Fraczyk, and He-Oh. This is also, in some sense, we have a related question. We had Sam's talk, and we combined this Edwards O and our result to obtain a result on the L2 eigenfunction for high-rank locally symmetric space. And yeah, we found this result quite surprising. So I'm going to also cover this one. Okay, so that's was my short introduction. All right, I'm going to move to the application now. So our application is going to be on the Corlette's conjecture. So I would like to start by explaining Corlette's conjecture. All right, so here's a reminder. So here's my setup. So G is going to be a semi-simple real algebraic group. And X is going to be an associated symmetric space. And you're going to take a discrete subgroup gamma inside G. And recall that we say a discrete subgroup is called convex cocompact if you can find a convex subset C inside the symmetric space on which gamma X cocompactly. All right, so we have seen several examples for this, but here are 3 examples that you might want to have in mind. So first example is Kleiner-Leeb group. So let me quickly draw this. So you have, you choose in H2, you choose a 2-player in H2 that plays ping pong dynamics, and if the contraction strength is strong enough, then you will see a ping pong picture, and you get a Kleinian-Schottky group. And in that case, what you're going to take is C is going to be this shaded region. And the second example is quasi-function subgroup. So you take a surface subgroup, gamma inside PSL to R, and you consider the embedding in PSL to C. So you have a circle which is invariant of the PSL to R, and you have a representation. Then the limit set is this. But now you deform gamma, then you will have some wiggly picture where the limit set becomes quasi-circle. In this case, the convex hull of this object. So you get this bumpy object with a bumpy boundary, and this is going to be your C. So in these two examples, I'm going to take C to be these two guys. And the final example is a cocompact lattice, which can be obtained by arithmetic construction. Okay, so two things to know. One thing to note is that these first two examples are in rank 1, and the only examples that are not lattice is coming from the rank 1 in this example. All right, so now there's a conjecture slash question of Corlette from 1994, where he asks, is there a genuine convex cocompact action in higher rank? So what do I mean by genuine action or non-trivial convex cocompact action? So here is a trivial action. So you're going to take G to be the product of two groups, G1 and G2. And G1 is going to be rank 1, and G2 is going to be possibly higher rank. Then you will take convex cocompact subgroup of rank 1, for example, like these two. And gamma 2 is going to be a cocompact lattice in the second vector. Then you can see if you write gamma to be gamma 1 times gamma 2, then it will act co-compactly on the associated symmetric space of Z in the most trivial reason. So this is not very interesting, and Corlette's question is asking whether there's other genuine action other than this one. And this was resolved by Kleiner-Leeb. I forgot, but it was 2000 something, 2006 or something. So Kleiner-Leeb says that this Corlette's conjecture is true, namely if you have a symmetric space X, and if you have a convex subset of this symmetric space on which you have a cocompact action, then the only way this can happen is the following. So your symmetric space X is going to be split as a product of two symmetric space X1 and X2. And your set C is going to be just a product of C1 and X2, where X1 is a product of rank 1 vector, and any other thing that is not any factor that is higher than whose rank is higher than 1 is going to be the factor is going to be X2. Okay, so this is Kleiner-Leeb's theorem, and independently, Jean-François.
Sorry, does it also say that gamma is a product of acting co-compactly on each factors?
Yes. But I'm going to explain it in the next slide. But independently.
Also here again with Zariski then.
Yes, Zariski dense. Thank you. But independently, using a different definition, Jean-François came up with a different proof. Jean-François came up with a different proof of convex cocompactness using a different definition. And this definition is going to take a similar form to our main theorem. So I'm going to explain this Jean-François theorem. Okay, so here's the setup. So you have Zariski dense discrete subgroup gamma inside G, and you're going to take A to be a maximal real split torus, or Cartan subgroup, and M is going to be a maximal compact subgroup in the centralizer of A. Now this set omega gamma is going to be important for us. So omega gamma is the following set. So you take the smallest closed subset, which contains all periodic orbits of all one-parameter subgroups of A. This means you choose one parameter subgroup on the Cartan subgroup, and then if you have a closed orbit, then you will put this inside your space. And if you choose a different one-parameter subgroup, you will also keep this periodic orbit inside. And if you do this, then this omega gamma is going to be, it can be defined for higher rank. But for example, if your group is of rank 1, then omega gamma in this case is exactly going to be this set C. It's going to be same as this one, which is a non-wandering set of geodesic flow. So here's theorem of Kang, which says the following. Oh, by the way, so here I wrote omega gamma to be the subset of G mod gamma mod M, but I'm going to, I can consider the lift of omega gamma to G, which is a gamma invariant set, and I'm also going to call it omega gamma for an aesthetic reason. Okay, so here is Kang's theorem. So suppose you have a convex cocompact action in this sense. So suppose omega gamma mod gamma is compact. Then the only way this can happen is that your G should decompose, your original group G should decompose as a product of simple Lie groups, G0, G1 up to GQ. And gamma should be decomposed as accordingly, where gamma I is going to be a subgroup of GI. And the point is that G1 up to GQ should be all of rank 1. And then gamma 1 up to gamma q is going to be a convex cocompact subgroup of rank 1 subgroups. And gamma 0 is going to be a cocompact lattice inside G0. So basically, you will see the analogy with the previous theorem of Kleiner-Leeb. And in fact, these two are interrelated. So Jean-François also gives a proof that his theorem can be used to prove Kleiner-Leeb's theorem that I mentioned earlier. Okay, so now the main theorem with Mikolaj Fraczyk is going to be provide a measured analog of this Kang's theorem. All right, so now I'm going to talk about a finite Bowen-Margulis-Sullivan measure. Okay, so Bowen-Margulis-Sullivan measure in the most classical setup was introduced in Margulis' thesis from 1970, where he studied and also flow on a compact manifold of negative curvature. And then it can be characterized in many different ways. So for example, it is a measure of maximal entropy in the classical case. And it's also a weak star limit of periodic orbit. So you consider, flow is anosoph, you have a lot of periodic orbits. You take the average of normalized measure supported on periodic orbits, and then take the weak star limit, then it's going to be converging to Bowen-Margulis-Sullivan measure. And there's a third description, which is given by a local product structure and Lie-Feist measure. And this is the viewpoint that I want to take for my definition later. All right, so here's a definition. Okay, I'm going to explain the definition, but I don't want you to take too much time on this because I might have time to explain this in detail. But for now, let's just, okay, let me just explain this. So what is a Bowen-Margulis-Sullivan measure? So it is going to be a measure on G mod gamma, first of all, and it's going to be an AM invariant measure. So we would say that this is a Bowen-Margulis-Sullivan measure if the following holds. So there should be a family of measure which is indexed by points in the base space, such as these following three condition holds. So first of all, these two measures are supported on stable foliation, leaf of the stable foliation, and then leaf of the central unstable foliation. So I did not write down what these are explicitly because on purpose, but okay, so WS stable is going to be stable leaf in our setup is going to be X N, and W center unstable is going to be X N A M. And plus and minus, depending on what you mean by n plus and minus. So this is, and then the second definition is what I want to call a conformality. So if you push forward your measure by A, then it just changes by a character of A. So chi of A is something, you can also write E to the some linear form phi log A if you, Okay. Yeah, okay. And then the third one is a local product structure. So M is going to be isomorphic to the product, this map. And this map, also I did not define this, but it's going to be a product map given by following the stable lift and the central unstable lift. So you have a, just takeaway is the following. So you have some conformality where you have, you know that it changes by a character, and then there's a local product structure. This is a two takeaway. All right, but there is a more hands-on definition that we saw in the previous course. It turns out that this construction is equivalent to the construction of measure on the boundary, so which was due to Paris and Sullivan in the case of the hyperbolic setup. But motivated by this construction, Kang constructed a higher rank version of Paris and Sullivan measure, which opens up a way to study higher rank discrete subgroup using the measure Paris and Sullivan theory. Okay, so for rank 1, you have critical exponent delta, and Paris and Sullivan constructed a measure which is delta dimensional. And for higher rank, the critical linear form means just a linear form that is tangent to the growth indicator we had before. In that case, you have for every critical linear form, Kang constructed a Paris and Sullivan measure supported on the limit set. All right. Did I start at 45? I forgot. 45. Okay, so this. Okay. All right. Yeah, maybe I should. Maybe I just write down what the definition of. Okay. Okay.
Does only the stable measure have conformality?
Oh, because you will get the other one. Yeah. All right. So hands-on definition is that you have this G mod M, then you have a Hopf parameterization which goes to pair of flag variety and then times A. Then you have so you have a natural map GM going to GP plus, GP minus, and some function that I'm not going to write down. And it's going to be locally equivalent to Patterson product of Patterson-Sullivan measure here, say nu sub maybe phi 1 and nu sub phi 2, and a loopback measure on A. And phi 1, phi 2 can be any linear form that has some conformal measure. And this is a generalized Bowen-Margulis-Sullivan measure, and there is a factor that will have to be put here, so to make all the thing gamma invariant. Okay, so this is, okay, so maybe I should write Bowen-Margulis-Sullivan measure is nu phi 1, phi 2 is going to be some measure which is equivalent to this local product. Okay. All right. Now I want to describe groups. I want to talk about what are the groups with finite Bowen-Margulis-Sullivan measure. So again, here are examples, 3 examples that you want to have in mind. So first example is geometrically finite subgroup of rank 1 group. So these are basically convex cocompact subgroup without allowing the cusp. Okay, so this is finite Bowen-Margulis-Sullivan measure, but this is not the end of story, because unlike the convex cocompact case, there are lots of geometrically infinite examples where your group is geometrically infinite but still have a finite Bowen-Margulis-Sullivan measure. So this example is due to Dalbo, Otal, Payne, and it's quite flexible construction. So you have really abundant examples even when your group is not geometrically finite or even not finitely generated. And the third example is coming from higher rank lattice obtained by arithmetic construction. And then except for this, no other constructions were known in higher rank. And you can imagine what our theorem should be now. So this is our main theorem with Mikolaj Fraczyk. So suppose we have discrete subgroup gamma which admits a finite Bowen-Margulis-Sullivan measure. with respect to any linear form. Then the only way this can happen is that G decomposes as a product of simple subgroups, G0 up to GQ, and gamma decomposes accordingly to this. And where G1 up to GQ is all rank 1, and gamma 1 up to gamma Q is a discrete subgroup of rank 1 group that has finite BMS measure, and G0 can have possibly higher rank, but gamma 0 should be cocompact, sorry, not cocompact, but lattice inside G0. So this is our main theorem. Okay, so I want to mention two corollaries of our theorem. So first corollary is really a special case. If you restrict your group to be a high-rank simple Lie group, then the previous theorem immediately implies that your Bowen-Margulis-Sullivan, your group will admit a Bowen-Margulis-Sullivan measure of finite mass if and only if gamma is a lattice. So this gives you a new criterion of detecting lattices in a high rank Lie group, a simple Lie group. And there is a second theorem that our theorem recovers Kang's theorem. And the reason
in the corollary one, and of course M has to be a higher measure in that case, right?
Yes.
By HBMS necessarily means, yeah.
Yeah, if M is finite, yeah, in this case, this BMS measure is going to be a higher measure. Yes, and then the second corollary is that the theorem, our theorem also recovers Kang's theorem because to prove Kang's theorem, we want to assume that this is compact, and we want to say that gamma is a cocompact lattice. But Bowen-Margulis-Sullivan measure, you can check that if it is finite, then it's going to be supported exactly on this set. So it's a locally finite measure supported on a compact set. You will give a finite measure, have a finite mass. So you can conclude that gamma is a cocompact lattice. All right. So now I have 30. Okay. All right. Do you have questions so far?
Can you show your theorem again? Sorry.
Yes.
Okay.
All right. If there's no question, then yeah, I would like to briefly mention about this bottom of L2 spectrum. So this is in joint work with Fraczyk, Sam Edwards, and Hill. So to motivate the bottom of L2 spectrum, I would like to, I pulled up a paper of Sullivan where he discusses this number, which is exactly the bottom of L2 spectrum. So there arises a number when you consider a non-compact manifold of negative curvature. And if you look at the Brownian motion and look at you look at how fast your Brownian motion escapes every compact set, then this is going to be described by some exponent, and this is exactly the bottom of L2 spectrum, which I'm going to define, which is the same as the one that you saw in Sam's talk. So, and the point of this Sullivan's paper was there are a lot of ways to see this number, a lot of different ways in certain circumstances, and we are going to take the spectral viewpoint as a definition. So here is a recap of the L2 spectrum. So you consider a hyperbolic metric on a hyperbolic space where you have this metric, and you consider a hyperbolic Laplacian. So here I'm taking this one. It's going to be negative definite, and for conventional reason, we're going to take a negative of Laplacian and look at the eigenfunction. So whenever you have a smooth function which satisfies this equation, you're going to call a lambda eigenvalue. And for conventional reason, I'm going to call the spectrum of Laplacian to be the one associated to this operator, unbounded operator minus Laplacian. So this is the spectrum of this Laplacian, and now the bottom of L2 spectrum is infimum of this spectrum. And by using the integration by part formula, you can write the bottom of L2 spectrum, which is lambda 0, to be the infimum of the following object, which is called the Rayleigh quotient. And yeah, it was observed by Sullivan that this bottom of L2 spectrum, in fact, is a threshold in the following sense. So you have a positive spectrum of Laplacian, and I did not define this. What does it mean to be a positive spectrum? So you look at this eigenfunction, but you don't require f to be L2. You just require that your f to be a positive function. And whenever your eigenvalue arises associated to this positive function, you're going to call this a positive spectrum. Now this lambda 0 is a threshold that if you look at this based on the bottom of the L2 spectrum, on the left you will only see positive spectrum, and on the right you will only see the L2 spectrum. So, and now the question we were asking was, is lambda 0 an atom? I mean, atom of the spectrum measure, or in other words, is eigenfunction associated to the lambda 0 is square integrable. This okay, so yeah, I guess I'm kind of going over this quickly because like Sam already did a like very concrete explanation of this. So observation is the following. So okay, so first, okay, so you consider a Patterson or gamma conformal measure nu, and there is a way to define a conformal density. Given a conformal measure, you can create a family which is indexed by the base point inside X mod gamma using this conformal measure. And just assigning the total mass of this gives a positive Laplace eigenfunction. This is one observation. And what Edwards and O did in their work is, this is some part of this, apparently. So you observe that positive L2 eigenfunction conversely can be always realized in this form for some gamma conformal measure. So that's first observation. And you saw the smearing lemma, which is due to Sullivan, was it Thurston as well? I forgot. Sullivan and Thurston. Yeah,
Sullivan says it should be called the Thurston theorem, but it could be called Sullivan and Thurston.
Okay, sorry. So I had to put Thurston. So for rank 1, this was due to Sullivan Thurston, and they prove this for a higher rank, and then you have this higher rank smearing lemma, which says you can associate Bowen-Margulis-Sullivan measure for, it doesn't have to be an A invariant measure actually. So here you consider a general Bowen-Margulis-Sullivan measure, no restriction on linear form, then you have this inequality. So you consider the total mass of Bowen-Margulis-Sullivan measure, it can be controlled by this integral given by the eigenfunction. So in particular, if you take nu and this to be nu1, nu2, that appears in the A invariant Bowen-Margulis-Sullivan measure, you will get these two functions is going to be they're going to coincide, and you can see that this eigenfunction is going to be if this is L2, then it means Bowen-Margulis-Sullivan measure is finite. So combining our two theorems will give you the...
But maybe small correction. I think the A invariant would mean that the nu1, nu2 has to be associated to the pair of linear forms which are given by the opposition involution relation, right? Yeah, but in the application we need when nu1 is equal to nu2, so it's...
yeah. Maybe should I answer this? How? Do I have 20? So we go. 25 minutes. Okay, I think okay, so yeah, so the opposition involution, so W0 is going to be a Weyl element, which is in the normalizer.
Can you recall? Can you recall what is M nu1 nu2?
Yeah. So I did not write the definition in the slide, but so M nu1 nu2 is, let's say nu1 and nu2 is gamma. Let's say this way. So nu1 is going to be gamma phi 1 conformal measure, and nu2 is gamma phi 2 conformal measure. then associated to any such conformal measure, you can define a generalized Bowen-Margulis-Sullivan measure. In the following way. So you have to define nu phi 1, nu phi 2, the density here. And the density is given by some expression. And it's going to be locally equivalent to this product of Lebesgue and conformal measure. And then here, basically the coefficient is given by Iwasawa cocycle.
Oh, okay, I see, I'm sorry.
Without any compatibility condition between 1 and 2?
Without any compatibility condition, but it's going to be A invariant if and only if phi 2 and phi 1 is related by some relation where this is called an opposition involution.
This means that the conformal factor is going to depend on the third coordinate in general.
Conformal factor is going to be, yeah. So conformal factor is
not being A invariant.
Yeah. So it will move by a character, which is like, okay, so this is, and for our application, we only need that these two are like same function. Okay. Okay, so we have, combining these two results, we have this theorem. If you have a high-rank semi-simple Lie group with no rank 1 factor, then if your group is an infinite volume, then you have no positive L2 eigenfunction, or lambda 0 cannot be the atom of the spectral measure equivalently. So this is note that this is a sharp contrast with the rank 1 case where you have lots of examples where this bottom of the L2 spectrum is realized as an atom of the spectral measure. For example, if you take a geometrically finite subgroup with a critical exponent greater than half of the dimensional boundary, then this is always an atom of the spectral measure. All right, so here are questions. I think Sam only mentioned the second one about the non-temperedness. So like we don't know any example of discrete Zariski dense subgroup where L2 G mod gamma is not tempered. And here's another other question we have in our paper, which asks, can there be any L2 eigenfunction any other than value of this bottom of L2 spectrum? This is widely open. And there could be more questions, but like this is like something you want to something you might want to know.
So, sorry, can you say again what this theorem says in question 1?
Positive.
And positive means what?
Sorry.
So the theorem says that there are no positive L2 eigenfunctions.
Yeah. Positive.
Yeah.
Means the function is positive.
Yes.
Not the eigenvalue.
No. Function is
yeah. So what our theorem says. What our theorem says, if there exists a positive L2 eigenfunction, sorry, no, I should not put it this way. If you have an infinite volume discrete subgroup of higher rank without rank 1 factor, then we don't have a positive L2 eigenfunction, which is same as saying because of this threshold. No, it's not because of threshold because you are in higher rank, but basically it's same as saying you don't have a L2 eigenfunction corresponding to the bottom of the L2 spectrum. That's
the only possibly positive one would be the bottom.
Yeah,
exactly.
Yes.
So if gamma is a finite volume, then there is, but it's just a constant.
Yes, right. Okay. Now I have I think like 20 minutes in principle. So I want to describe the idea of the proof. The idea of the proof, I'm going to give you a proof for two cases. The first case is when G is a simple high rank group. And second case is when G is a product of two groups, and gamma is an irreducible subgroup in the sense that your projection to each vector is dense. In that case, our strategy is to show the following. So we want to show that if your BMS measure is finite, then BMS measure is invariant under the whole group, meaning it's a hard measure. If you have a hard measure that is finite, then this is exactly what it means for your group to be a lattice. So this would imply that gamma is a lattice, right? Clear? All right, so now I have to give a recap of, okay, so before I get to this, so our technique is to use the high entropy method together with the entropy product structure of Einstein-Katok and Einstein-Katok-Lindenstrauss. And for that, I have to recall you the definition or some properties of leafwise measure. So leafwise measure, what is definition? So you consider locally finite Borel measure. You can consider it in a more general setup, but for us, it's going to be G mod gamma. Now you consider a closed subgroup S inside G, and you consider, you're going to call, okay, so there exists a leafwise measure, what is called leafwise measure associated to this mu. It's going to be indexed by points in the base space. And locally can be described as follows. So here is a picture from a piece of note by, written by Einstein and Lindenstrauss. So here, what you're doing is you consider some point inside G mod gamma, and you take a cross section C. You take a cross section and you look at the leaf, which is the orbit of S. So if you have this picture, and you can consider locally conditional measure, which is a measure that's living on the leaf of the measure. So if you have mu, you want to pick up the measure that lives here. And then it's going to be given as locally as a conditional measure along the leaf. But what you're actually constructing is a measure that lives on the subgroup, not on the leaf. So mu xs is a measure that lives on S. Okay, clear so far? All right. So Einstein-Katok and Einstein-Katok-Lindenstrauss, we're going to use two of the results, which is high entropy method and entropy product structure. So let me explain what these are. So high entropy method means the following. So suppose our G is SL3R, which is a simple Lie group, and you consider the 3×3 matrix. I'm going to call this unipotent subgroup U12, at least one U13, U23. The higher entropy methods is the following. Oh, okay, so sorry. Before that, let me explain all the observation. So remember, you can consider, for any subgroup, you can consider a leafwise measure associated to that. So I'm going to consider a leafwise measure associated to each subgroup, which I'm going to call a root subgroup. So mu x u I j, there are three possibilities in this picture. So there are two extreme cases. Remember, this is a measure that lives on the group. The two extreme what are the two extreme cases? One extreme is that this is a trivial, in the sense that this measure is a Dirac mass supported at the identity. So you have a group, you have an identity. One case is that this measure is supported on the identity. And the other extreme is that this is in fact a hard measure on Uij. So there are two extreme cases. And these two extreme cases actually tells you about something global for the measure mu. So for example, if this is trivial, it will mean that your measure mu will have a global cross section. Global cross section, which has, and then for second one, if mu x uij is hard, then this will mean that the original measure is invariant under this subgroup uij. All right, so what is high entropy method? It is the following. So you look at this commutator. If you take the commutator u12 and u23, then you get u13. That's by matrix computation. So geometrically, this means that the leaf, these two leaves are not jointly integrable. So if you go around u12, u23, and the other way, you get a mismatch. And high entropy method tells you that this mismatch under some, if your leaf-wise measures, you started with a non-trivial leaf-wise measure, this mismatch will give you an invariance of your original measure. So for this simplest example, if this is non-trivial and the second one is non-trivial, you can harden, meaning they will give you that if you have this one non-trivial, you take the commutator, this one is going to be hard, meaning that your original measure is invariant or U13. So in this way, you get some invariance. So this is called a high entropy method. I mentioned entropy product structure as well. So what is entropy product structure? So this high entropy method is in fact born from the entropy product structure. So entropy product structure is the following. So if you have a group which is a semi-direct product, okay, so let me not explain the very general setup, but you should think of this H as a horospherical subgroup N, and T and U as root subgroup and the remaining part of the subgroup. Then entropy product structure tells you that you have, under mild recurrence assumption, you have this product structure. This is due to Einstein-Katok. Now, how does this help us? So now I can fit the proof in one slide for the, okay, maybe that's a bit light, but the strategy is the following. So we're going to consider the entropy product structure of Einstein-Katok, Lindenstrauss. So from this you get, if you have a finite BMS measure, you get an entropy product structure. So that's one thing. And remember that I was emphasizing when I gave this definition of Bowen-Margulis-Sullivan measure, I emphasized the condition 2 and 3. 2 was conformality, 3 was a local product structure. So this existence of local product structure is something that is genuine from the beginning, whereas the product structure of Einstein-Katok is what you obtain by this EKL method. Now you're going to compare these two information. You have two product structure. All right, so remember that I'm going to give you two cases. The one proof for the first case when is G is simple. When G is simple and of high rank, then there are two cases. Okay, so the case one is that if you look at the leaf-wise measure associated to this BMS measure with respect to the horospherical subgroup, then first case is going to be either supported on a Zariski closed subset of N. This is one possibility. Or if not, you will get an invariance. In fact, by comparing these two product structure, you don't get just small invariance, you get an invariance under all root subgroup. All root subgroup meaning that your measure is going to be invariant along the whole G, meaning that your group is hard, okay, gamma is a lattice. And the first case can be excluded solely by using the Zariski density of your discrete subgroup. All right, so what goes for the second case when you have a product of group and gamma is irreducible, again, in the sense that it has a dense projection to each vector. In this case, we don't use high entropy method. Instead, you're still going to appeal to the entropy product structure. So I didn't say very explicitly, but you will have to use entropy product structure in a very strong form in the first case as well. All right, so let's focus on this case. Now you have a product of two groups and gamma is irreducible discrete subgroup in the sense that it has a dense projection to each vector. Now, in the definition that I used for M, there was a conformal measure hiding, which is very explicit in the hands-on definition. So there is a gamma conformal measure attached to your BMS measure, which is nu phi 1, nu phi 2 here. Now, if you apply the entropy product structure, what you can prove is that your leaf-wise measure, maybe mxn, this should decompose as a product of two measures. And using conformality, what you can say is that the after you decompose, what you see in each vector should be also conformal. Not genuinely conformal, but I say almost conformal. In fact, it's going to be conformal under the commutator of gamma. But if gamma is like Zariski dense, taking commutator, but what you know is that gamma has a dense projection. But if you take a commutator of these two, you will also get a dense thing. So what have we learned? So you have some measure is some product of, I don't know, maybe this is a bad notation, but I'm just improvising. So this is a conformal measure, and then this breaks into two conformal measure, and this is conformal under the pi 1 gamma. This is conformal on the pi 2 gamma. And pi 1 gamma, let's just think of this as a Peretz-Sullivan measure. I'm not lying too much when I do this. So you have a conformal measure which is conformal with respect to pi 1 gamma, but pi 1 gamma is dense. So by continuity, you have G1 conformal measure and G2 conformal measure. But it's not hard to see that the only measure, such measure, is R on the boundary. So yeah, this is our idea. And okay, so like going back to my question. Okay, I mean, you can sort of felt that maybe my definition of large is discrete subgroup with finite Bowen-Margulis-Sullivan measure. But why didn't I put it that way? Because you like to find like future application of this method. Hopefully, like, I don't know, maybe we'll be able to say something more. And then in that case, we can upgrade our definition of largeness. All right, so thank you for your attention.
Any questions? Yes. Yeah.
So somehow your theory, it's maybe a late question, but somehow your theorem is, you said that it's an analog of measurable analog of the fact that there is no convex cocompactness in higher rank. However, in higher rank there is a theory of Anosov representation, which is a fairly good analog of convex cocompactness. Do you think that there is a measurable analog of it? Or yeah.
Sorry, I don't think so, okay, maybe I did not, there's...
I mean it's, you have these Patterson-Sullivan measures, and you're proving that, I mean, if you take a group which has infinite covolume, they will never have a finite covolume, but still could there be some other, I don't know, some measurable condition that would be the analog of having finite covolume in rank 1, and that would...
sorry, just because I'm like slow at understanding. So your question is, okay, so you have an subgroup which is a generalization of convex cocompact group, and then
just asking if do you think there is a measurable analog of Anosov representation?
I think his theorem says that we have to work with the infinite BMS measure in that case.
Sorry?
But also you can say in Anosov case, actually, all these BMS measures have infinite mass. This was known due to San Marino. So, but,
yes, but still
we
they
have an
exist.
infinite BMS measure, but we work with it, right? Because there all this local mixing theorem for infinite BMS measure. So you should just give a finite BMS measure, but you have to work with the infinite BMS measure. That's, yes. I think.
And
that's
so
what
now the question
says.
is, even if the BMS measure is infinite,
yes,
would there be a condition that would be something weaker than Anosov, but still an interesting condition, which would be
like for instance, if you have a local mixing or organic, that's a good condition for a measure to have, right? Like, I think. I mean, like if you have a BMS measure which is organic, which is known for say Anosov, but could ask you, organicity or mixing.
Although there is another BMS measure, because here what we took was sort of limit sets times limit sets times A, and you can replace A by R instead.
Yeah.
And then
if you have a fiber part of the picture, right?
And then finite BMS measure there
But can you do that for any finitely generated group?
Read what I wrote, what I sent you, Nico.
Yeah, you need to work that.
Right, I guess one could ask if there is this 5 on the measure picture, then does it imply it's not so for like some special class of discrete groups? Maybe, yeah, that can be answered.
Any other questions?